Hello my friends and welcome back to KrossUSA. Today we're diving deep into the fascinating world of modern infrastructure construction. So grab your hard hat, metaphorically speaking, and let's explore some of the most impressive construction feats of our time. Our first stop takes us to an impressive infrastructure project that demonstrates Turkish engineering excellence at its finest. The bridge, constructed by the renowned Gulsan Holding, represents a perfect blend of innovative construction techniques and robust engineering principles. This isn't just another bridge. It's a testament to what modern construction companies can achieve when they combine traditional expertise with cutting-edge technology. Nang Gulsan Holding, established in 1961, has been a powerhouse in Turkey's construction industry for over 6 decades. The Nisibi Bridge project showcases their evolution from a traditional construction company to a technology-driven engineering firm. This bridge serves a critical role in regional connectivity, designed to handle substantial traffic loads while withstanding the challenging geographical and climatic conditions of the region. NTHE project required careful consideration of seismic activity, weather patterns, and environmental impact, factors that significantly influenced both the design and construction methodology. What makes the Nisibi Bridge construction particularly fascinating is Gulsan Holding's deployment of integrated construction management systems. The project utilized advanced building information modeling, or BIM, technology from the ground up, allowing engineers to simulate every aspect of construction before breaking ground. NTHE heavy lifting was handled by state-of-the-art mobile cranes, including Liebherr LTM series cranes capable of lifting over 200 tons. For concrete work, they deployed automated concrete pumping systems with boom lengths extending up to 65 meters, ensuring consistent concrete placement even at significant heights. Perhaps most impressive is their use of GPS-guided pile driving equipment. These machines can position foundation piles with millimeter precision, critical for a structure that must maintain perfect alignment across spans of hundreds of meters. The real-time monitoring systems continuously tracked structural stress, temperature variations, and settlement patterns throughout construction. The construction sequence began with extensive soil analysis and foundation preparation. Using rotary drilling rigs, crews installed deep foundation piles reaching depths of up to 40 meters. Each pile underwent rigorous load testing to ensure it met the bridge's demanding specifications. NTHE superstructure construction employed a segment-by-segment approach using precast concrete elements. This method offered several advantages: better quality control and controlled factory conditions, reduced on-site construction time, and minimal disruption to local traffic patterns. NTHE's most spectacular phase was the installation of the main spans. Using the balanced cantilever method, construction crews worked from both sides of each pier simultaneously, maintaining structural balance as they progressed toward the center. This technique requires incredible precision. We're talking about tolerances measured in millimeters across spans of over 100 meters. Cable-stayed elements were installed using specialized strand jacking equipment, with each cable tensioned to exact specifications using computer-controlled hydraulic systems. The entire process was monitored in real time using strain gauges and displacement sensors. One of the most innovative aspects of this project was Gulsan's implementation of smart construction techniques. They utilized IoT sensors embedded throughout the structure to monitor concrete curing conditions, automatically adjusting heating and cooling systems to optimize strength development. Weather presented significant challenges, particularly during the concrete pouring phases. The team developed contingency protocols using rapid-setting concrete additives and temporary enclosure systems, ensuring construction could continue safely even during adverse conditions. This level of preparation and technological integration exemplifies modern Turkish construction capabilities on the global stage. Now let's travel to the stunning Canary Islands, where engineering meets paradise. The Aircase Viaduct, located in southwest Tenerife on the new route from Adeque to Santiago del Teide, represents one of the most challenging bridge construction projects in recent European history. This isn't just about connecting 2 points. It's about bridging dramatic volcanic terrain while preserving one of the world's most unique ecosystems. NTHE project faced extraordinary challenges: volcanic soil conditions, extreme wind loads from Atlantic weather systems, and the need to minimize environmental impact in a UNESCO-protected landscape. Construction in volcanic terrain presents challenges you won't find anywhere else. The Irkes Valley features layers of volcanic ash, hardened lava flows, and unstable scree slopes, a geologist's nightmare and an engineer's ultimate test. Traditional foundation techniques simply wouldn't work here. NTHE solution: innovative micropile foundations that penetrate through unstable volcanic layers to reach bedrock. These specialized piles, only 200 to 300 millimeters in diameter but incredibly strong, were installed using track-mounted drilling rigs specifically designed for steep, unstable terrain. An environmental protection added another layer of complexity. The construction zone includes habitats for endangered species and rare volcanic plant life. Every piece of equipment, every construction sequence, and even the timing of work shifts were coordinated with environmental biologists to minimize ecological disruption. The viaduct's construction utilized the incremental launching method. Imagine building the entire bridge deck on one side, then literally pushing it across the valley using hydraulic jacks. This technique reduced the need for temporary supports in the environmentally sensitive valley floor. NTHE bridge deck, constructed in 30-meter segments, weighs approximately 450 tons per segment. Specialized launching equipment, including nose beams and sliding bearings, guided each segment as it was pushed across spans reaching up to 85 meters. The process required millimeter-precise alignment and constant monitoring of structural stresses. What's particularly impressive is the wind resistance engineering. Atlantic storms can generate winds exceeding 150 kilometers per hour, so the bridge incorporates aerodynamic shaping and tuned mass dampers to prevent dangerous oscillations. Computer modeling using computational fluid dynamics ensured the structure could handle the worst weather conditions the Atlantic could deliver. Nente, the completed Irkes Viaduct, stands as a masterpiece of environmental engineering, reducing travel time between Adeje and Santiago del Teide while maintaining the pristine beauty of the Canary Islands landscape. It's a perfect example of how modern construction can work in harmony with nature, creating infrastructure that enhances rather than dominates the natural environment. Hold on to your seats because we're about to explore one of the most ambitious bridge projects in modern history. The Çanakkale 1915 bridge, spanning the Dardanelles Strait in Turkey, isn't just the world's longest suspension bridge, it's a monument to human engineering ambition. With a main span of 2,023 meters, this bridge pushes the boundaries of what's physically possible in suspension bridge construction. And let's talk numbers that will blow your mind. The main towers soar 334 meters into the sky. That's taller than the Eiffel Tower. The bridge uses over 45,000 tons of structural steel and consumed more than 160,000 cubic meters of concrete. But here's what's truly remarkable. The main cables contain over 11,000 individual steel wires, each precisely tensioned to support the bridge's massive loads. NTHE construction required specialized equipment on an unprecedented scale. The floating cranes used for tower construction could lift over 1,000 tons, while the cable-spinning equipment represented the latest evolution of technology, first developed for the Golden Gate Bridge nearly a century ago. Wind tunnel testing was crucial. Models were tested in facilities across 3 different countries to ensure the bridge could handle the notorious winds of the Dardanelles Strait, which can exceed 200 kilometers per hour during severe storms. The tower construction process was engineering poetry in motion. Using the climbing formwork method, construction crews built the towers in 4-meter increments, with specialized climbing systems that automatically repositioned themselves as the towers grew skyward. This process required absolute precision. Any deviation from vertical would be magnified enormously at the tower tops. NTHE's most spectacular phase was the main cable installation. Using the air-spinning method, specialized machines traveled back and forth across the strait, laying individual wires with mathematical precision. End-deck installation used the lift-and-place method with custom-built floating cranes. Each deck segment, weighing up to 750 tons, was lifted from barges and positioned with GPS-guided precision. The segments were then welded together to create the continuous roadway, with expansion joints designed to accommodate thermal movement of up to 2 meters. An NTHE project also incorporated seismic isolation systems, given Turkey's location in an active earthquake zone, ensuring the bridge can withstand major seismic events while maintaining structural integrity. Welcome to the future of transportation. Today we're diving deep into the construction of high-speed railway infrastructure capable of supporting trains traveling at 350 kilometers per hour. This isn't your grandfather's railroad. We're talking about precision engineering that rivals spacecraft construction, where tolerances are measured in millimeters and safety margins are absolute. NTHE star of our show is the SL932 Bridge Girder Erection Machine, a technological marvel that represents the pinnacle of railway construction equipment. This beast of engineering can handle bridge segments weighing up to 900 tons while maintaining the surgical precision required for high-speed rail infrastructure. NHIG H-speed rail construction demands perfection. At 350 kilometers per hour, even microscopic imperfections in track alignment can cause catastrophic failures. Every element, from foundation preparation to final track installation, must meet tolerances that would challenge the most sophisticated manufacturing processes. Let's get acquainted with our mechanical star, the SL932 Bridge Girder Erection Machine. This incredible piece of equipment represents decades of engineering evolution, specifically designed for the unique demands of high-speed railway construction. NTHE machine spans an impressive 140 meters in length and can lift loads up to 900 tons. That's equivalent to lifting about 600 automobiles simultaneously. But raw lifting power is just the beginning. The SL932 incorporates precision positioning systems that can place massive concrete girders with accuracy measured in single millimeters. NTHE machine operates on a fascinating principle. It travels on the very railway it's helping to construct. Using specialized rail cars, it moves along completed sections while extending its massive lifting apparatus over the construction zone. The counterweight system is particularly ingenious. As it lifts a girder at the front, the machine's weight distribution automatically adjusts to maintain stability. GPS guidance systems work in conjunction with laser positioning equipment to ensure each girder placement meets the exacting standards required for 350 kilometers per hour operation. We're talking about positioning accuracy that surpasses what's required for precision manufacturing, except we're doing it outdoors, in all weather conditions, with structures weighing hundreds of tons. Before we dive into construction details, let's understand what makes high-speed railway infrastructure so demanding. At 350 kilometers per hour, aerodynamic forces become critical design factors. The track structure must not only support the train's weight, but also resist the powerful air pressure waves generated by high-speed passage. NTHE foundation systems extend much deeper than conventional railways, typically 3 to 4 meters below grade, compared to less than a meter for traditional rail. This deep foundation system prevents settlement and maintains the precise geometry essential for high-speed operation. We're dealing with tolerance specifications of plus or minus 2 millimeters for track alignment. Imagine maintaining that precision across hundreds of kilometers. Bridge structures for high-speed rail incorporate sophisticated vibration damping systems. As trains pass at extreme speeds, they generate resonance frequencies that could cause dangerous oscillations in conventional bridges. The solution involves tuned mass dampers and carefully calculated structural stiffness that prevents harmful vibrations while maintaining the flexibility needed to accommodate thermal expansion and seismic movement. NTHE electrical systems are equally demanding. High-speed trains draw enormous amounts of power, up to 15,000 volts, requiring overhead catenary systems with unprecedented precision in wire positioning and tension. The construction process begins with foundation work that resembles archaeological excavation in its precision. Using GPS-guided excavation equipment, crews remove soil to exact depths, often requiring specialized dewatering systems to handle groundwater in below-grade construction zones. Foundation piles for high-speed rail bridges are engineering marvels themselves. These aren't simple concrete cylinders. They're precisely engineered structures with internal reinforcement patterns designed using computer modeling. Rotary drilling rigs install these piles to depths that can exceed 50 meters, with each pile subjected to rigorous load testing that simulates decades of high-speed train passage. NTHE concrete work requires specialized techniques rarely seen in conventional construction. Self-consolidating concrete, which flows like thick syrup but cures to incredible strength, ensures complete filling of complex reinforcement patterns. Temperature control during curing is managed using embedded cooling systems. Massive concrete pours generate significant heat that could cause cracking if not carefully managed. Perhaps most impressive is the precision surveying throughout this phase. Every foundation element is positioned using real-time kinematic GPS systems with accuracy measured in millimeters. Laser scanning equipment continuously monitors the work, comparing actual construction to the theoretical design with tolerances that would challenge precision manufacturing. The concrete girders handled by our SL932 machine are manufactured off-site using industrialized production techniques that ensure consistency and quality impossible to achieve in field conditions. These aren't simple concrete beams. They're precisely engineered structures with complex internal geometries designed to optimize strength while minimizing weight. Each girder incorporates post-tensioned cable systems that compress the concrete, dramatically increasing its load-carrying capacity. The post-tensioning process involves hydraulic jacking systems that stretch high-strength steel cables to predetermined loads, then anchoring them to maintain permanent compression in the concrete structure. Transportation to the construction site requires specialized heavy-haul trailers with sophisticated suspension systems. These trailers can weigh over 200 tons when loaded, requiring careful route planning and sometimes temporary road reinforcement. GPS tracking systems monitor the girders during transport, ensuring they don't experience stress levels that could cause microcracking. Quality control throughout manufacturing and transportation involves non-destructive testing techniques, including ultrasonic scanning and ground-penetrating radar to verify internal structure integrity. Every girder receives a digital passport documenting its entire history from manufacturing through installation. Now comes the spectacular part. Watching the SL 930 seconds in action is like observing a precision dance performed by a machine weighing thousands of tons. The installation process begins with careful positioning of the machine itself, using guide rails that maintain perfect alignment with the bridge structure under construction. NTHE girder pickup process is mesmerizing. Using specialized lifting beams that distribute loads evenly across the girder's length, the machine's hydraulic systems engage with mathematical precision. Load sensors continuously monitor stress distribution, ensuring the girder experiences only the forces it was designed to handle. The Fortune-Hersign transport across the construction zone requires incredible coordination. The machine moves at speeds measured in centimeters per minute, with constant monitoring of girder stress, machine stability, and positioning accuracy. Gyroscopic sensors detect any unwanted movement, immediately triggering corrective adjustments through the machine's sophisticated control systems. NTHE placement process pushes engineering precision to its absolute limits. Using laser guidance systems and GPS positioning, the girder is lowered into position with tolerances measured in single millimeters. Temporary supports engage automatically as the girder reaches its final position, followed by connection procedures that create monolithic structural continuity. Weather monitoring systems continuously track wind conditions. Operations cease if wind speeds threaten the machine's stability or positioning accuracy. The entire process from pickup to final placement can take 6 to 8 hours for a single girder, but the result is positioning accuracy that meets the demanding requirements of 350 kilometers per hour railway operation. Quality control for high-speed railway construction operates on levels that rival aerospace manufacturing. Every installed girder undergoes comprehensive testing using specialized railway testing vehicles that can detect imperfections invisible to human inspection. Dynamic testing involves specially designed test trains that traverse completed sections at various speeds, monitoring track response using accelerometers and displacement sensors. These tests can detect structural issues that might not manifest until years of service, allowing correction before the railway enters commercial operation. Non-destructive testing techniques include ground-penetrating radar scans that verify internal concrete structure, ultrasonic testing of connection points, and laser scanning that creates three-dimensional models with millimeter accuracy. Any deviation from design specifications triggers immediate investigation and corrective action. NTHE final verification involves high-speed test runs with production railway equipment, gradually increasing speeds while monitoring hundreds of parameters including vibration levels, noise generation, and electrical system performance. Only after passing these exhaustive tests can a section be certified for 350 km per hour operation. Modern high-speed railway construction incorporates environmental protection measures that would have been unimaginable in earlier eras. Noise barriers aren't afterthoughts. They're integrated into the structural design from the beginning, often incorporating advanced materials that provide both acoustic dampening and structural support. Wildlife protection involves sophisticated crossing structures that allow animal migration patterns to continue uninterrupted. Some installations include dedicated animal bridges with natural vegetation that provide safe passage over high-speed rail corridors, and construction safety protocols rival those found in nuclear facility construction. Worker safety systems include continuous air quality monitoring, automated equipment shutdown systems if personnel enter dangerous zones, and emergency response capabilities that can mobilize medical assistance within minutes. Environmental monitoring continues throughout construction, tracking everything from groundwater levels to air quality. Dust suppression systems use recycled water and biodegradable additives, while noise control measures ensure construction activities comply with strict community standards, even during intensive operation periods.